Logarithmic functions. Logarithmic functions, one thing you need to keep in mind as we're doing logarithms, a logarithm is an exponent. That is a simple truth that simplifies and helps you memorize some of the aspects of logarithms. So if you can remember that a logarithm is an exponent, that can help us in a lot of areas here. One of those areas is the first little definition we have with logarithms. It's the equivalencies of logarithms. So log base A, so that means the base, like when you're thinking exponentially, we just talked about exponential functions last couple of days. The base, like that would be 2 to the x power. The base is 2. So when we say log base 2, we're talking about that base. When we're thinking exponentially then. B is equal to C. What that is equivalent to is an exponential statement. So we have a logarithm is equal to an exponent. That's what that statement says. A logarithm is an exponent. In math, is means equals, right? So a logarithm is an exponent. So the exponent here is C. The base is whatever base this log is. So A to the C power is equal to B. That's the equivalency. And we're going to use this. It's going to help us solve some equations, take some logarithmic equations, and turn them into exponential equations. And then it's something we already know how to do. And so we're going to look at those today. So that rewriting a logarithm as an exponential is our first order of business. Rewrite the logarithm as an exponential. And then we'll go the other direction. Step away. Y is equal to the log base 3 of x. Thank you very much. All right. So if we're going to rewrite that as a exponential, we look for the base of the log. So the base, log base 3 is how you read that. So the base is 3. Which one of those is the exponent, the y or the x? The y. Whatever it's equal to is the exponent. So when we rewrite that, it's going to be 3 to the y power is equal to x. And you've rewritten a logarithm as a exponential. Simple stuff. Not any work to do here. Just simple manipulation is all it is. Okay, so this one would be 2 as the base because it's log base 2. So 2 to what power? Third is equal to x. That would, if we can do that, that would allow us to figure out what x is, right? We know what 2 to the third is, right? We know x would be 8 if that were an equation we were asked to solve, something like that. So being able to rewrite from a logarithm to an exponential can help us solve some things later on. C, log base 5 of 1 over 25 is equal to x. Again, rewriting that as an exponential. What's the base? 5, the exponent, x, is equal to 1 over 25. And that looks like an equation that we just got through solving. So the idea here is that if we can rearrange a logarithm into an exponential, maybe we already have the skill set to solve those based on what we've already done. I may have said this in this class before, but may not have. One of the keys to being a good mathematician is making things look like things you already know how to do. And that's what we're doing here. Where some knowledge comes in, a little head knowledge here, ln of x is equal to y. And anybody remember what ln is from natural log? It's actually log base what? No. E.
I was going to get to that number.
You passed it when you got the 3. Dang it. All right, so it's natural log is log base e. So when you see natural log, think this and say, oh, well, it's e to the y is equal to x. Natural log is log base e. Now here's the question everybody was answering. Log of x is equal to 3. What's the base? Log base is 10. If they don't write it there, it's an understood 10. Okay, and the reason it's an understood 10, what number system do we live in all of the modern world? The 10, base 10 number system. Each position in numbers, the ones position is 10 to the 0 power, the tens position is 10 to the first power, the hundreds position is 10 to the second power. That idea, we're in the base 10 world. So this is a common log. Natural log and log base 10 are common logs, is what they're called. So it's a log base 10 here when they don't write it there. So that it would be 10 to the third power is equal to x. And again, that'd be an example of one that we could actually, we quickly solve just by rewriting it and not really doing any hard, difficult mathematics to get an answer, just rearranging. Amanda?
Why does it become like more efficient to have something?
The idea of logarithms is to take extremely large numbers and make them more manageable, because like 2.3 times 10 to the 75th is more manageable than writing out 2, 3 and then 74 zeros after that, right? So the idea of logarithms is to take numbers that are extremely large, make them manageable, or take numbers that are extremely small, like a 0.32 zeros and then a number, and change it. And so it's logarithms help us take those extremely large numbers and do that. Now, as far as when is it more efficient equation wise, depends on the numbers that are involved and the base that you're dealing with. Because if here we had a base 10 and a 3, so it works out really easy here. But if this was if the x was over here and this was a base 4, finding that number, it's not as quite as easy. Depends on the numbers. Which one's more efficient, which way to do that. Today, we're going to focus mainly on rearranging logs and exponentials and getting those worked out. But when we get into equations, the next section after spring break, we'll see, okay, well, this is when we need to do this. This is when we need to do that. And there are some properties involved that we'll use. So it just depends on the numbers in the problem. Good question, though. All right. All right, let's go the other direction. Let's rewrite as a logarithm. Rewrite the exponential as a logarithm. Three to the x is equal to 27. Again, we know enough about exponential equations that we could solve that if we needed to, because the numbers are nice, but that doesn't necessarily always work there. So what's the base in this exponential? 3. So we're going to use log base 3 of 27 is equal to x. Remember, the logarithm is always going to be equal to the exponent. Okay, so that's the key. Here we have 10 to the x plus 1 is equal to y. Rewriting that as a logarithm. I know it's equal to the exponent, so that's the x plus 1. What base is that? 10. Do I need to write the 10 there? No. Is it wrong if I do? Not necessarily, no. So that would be log base 10 of y is equal to x plus 1. If you wrote the 10 there, that's okay. But it's not normally done. Kind of like writing the 1 in front of x. You know it's there, but you don't usually write it there. A to the 4th is equal to 24. What's the base on this one? A. Log base A of 24 is equal to 4. Five to the x is equal to 625. Log base 5 of 625 is equal to x. E to the square root of x is equal to y. What log is that? Natural log. So n of y. Now, if you wrote log base e, I would not accept that. Log base e is natural log, so use the LN there to help you do that. Okay. All right, so just rewriting from logs to exponentials, from exponentials to logs. Be able to do that. That's not a hard thing. It all goes back to bases and exponents. All right. Next thing what we might be asked to do is to evaluate some logarithms with and without a calculator. So evaluating with or calculators, monkeys can do. Without a calculator, I'm not sure they can. They can't talk, so they can't tell us the answer. So they may be able to do it, but we'll never know unless they learn. Well, there are monkeys that learn sign language, so maybe they could. Let's look at log base 2 of 16. So there's our equation. They say evaluate that, and so let's focus mainly on evaluating without a calculator first, and then I'll show you how to punch these in the calculator to check and evaluate ones that are not easy like this. Okay. Now, I know that log base 2 means that I'm thinking, okay, if I'm going to evaluate that, I'm going to find out what that's equal to, right? That's what evaluate means. And so I'm looking for what it's equal to. It should be equal to a what? An exponent, right? So the idea is that if I think, okay, it's some sort of exponent over here. So it's a base of what? 2. So we're really thinking 2 to what power is equal to 16. So it's taking something that they didn't write this equals x on there, but I'm thinking that as I'm going here, and I'm like 2 to what power gives me 16? And you guys know that that's, oh, Hunter's trying to confuse people up here. Okay, so when it's a nice number there, that's an easy conversion, right? When it's a good number. Let's look at this one. Also a pretty decent one. Evaluate log base 4 of 1/64. Well, we know that we're looking for the exponent when you raise what to this exponent. What's the base? 4 to the x is 1/64. So we're evaluating that, and we're thinking about it like we did in section 3 with exponentials. 4 to what power is 1/64? -3. And you guys have done several of these, so you know kind of what's going on there. And if you needed to manipulate it a little bit and write it as 4 to the negative third, and then get your equation there, that makes it work out.
May I have your attention, please? I need the following students to the library, please, for testing. Hunter Brown, Ty Case, Jaden Crum, Hannah Curtis, Logan Frazier, Kaylee Kemper, Colin Leffler, Clayton Moore, Jeremiah Neal,
All right, so
Robert Sexton,
log base 3 of
Andrew White,
81. Again,
Jackson
this is a
Riley
nice
Watkins,
number. We know a lot about 81. We know a lot about
Tommy
3.
Sessley, Danny
You know, so
Turbin,
it's
Tyler Butler,
3 to
Dylan
what
Haggins,
power gets me
Alexis
81?
Hazel, Dalton Meek, Chipper Milligan, Isabella Purvis,
4,
Emily
right?
Thompson, Skylar Wilbanks, Haley Williams,
Okay, so being able to evaluate those without a calculator, the numbers have to be kind of nice. Okay, I'm going to show you.
Caitlin Reed, Abel Wolf, Z Atkins, Josh Butler,
Eventually.
Caitlin Cooksey, Amanda Davis, Casey Duncan, Hunter Holcomb, Spencer Hurst, Gage Luke, John McAfee, Carver Orso, Parker Smith, Dexter Worley, Anna Kate DeBerry, Caleb Chenault, Justin White, Katie Lindsay, Taya Ditto, Kara Helms, and
All right.
Jackie Weatherly.
So this one, we have log base 3 of 24. I'm just going to talk about it.
To the library.
So we have the base 3 and the 24. What do we know about 24? That it's not 3 to a power, right? If it were 27, yeah, we got a great one to work out there. So that's not quite as easy to manipulate there. So that's where being able to evaluate these with the calculator comes in. So we'll show you example M and N both with the calculator and show you what you're doing there. So your graphing calculator has some neat features to it that not all scientific calculators have. That feature is the log base feature, which you hit the math button. You press the up arrow because it's down toward the bottom, and we're looking for log base. So just hit enter on log base, and it should give you this where you can type in what base you have and then the number. Okay. Hopefully this is not news to you. You knew this in Algebra 2. Hopefully. If you didn't, then you could have made better grades in Algebra 2 had you known this. All right. So base 3, and if I put the 81 in there with like example M, it cranks out the 4 out of that. That's nice. If I do the same thing, math, log base 3 of 24, can we kind of estimate where that should be? It should be between what two numbers? 2 and 3, because we know 3 to the second power is 9, 3 to the third power is 27. It should be closer to 3 than it is to 2, because 24 is closer to 27. So, but we punch that in there, and there we get 2.8929 or 28. Let's go 4 decimal places. 2.8928. Now, if for some reason you're not in a world where you have that log base feature on your calculator, you don't have that calculator, maybe you're stranded somewhere and all you have is a calculator on your phone, it doesn't have the log base feature. So you need to be able to manipulate a log and evaluate that, because that's the only way you're going to get off the desert island is being able to manipulate logarithms, right? So the key is that change of base formula. And the change of base formula allows you to take a log of any base and convert it into a common log setup. So the common log would be log base 10 of y over log base 10 of x. Or you could use the other common log, natural log of y over natural log of x. Sometimes it's quicker for me to just type that into the calculator that way instead of hunting the log base feature. Okay. If on the calculator, on the left-hand side, every scientific calculator has this. Your phone calculator, when you turn it or the iPhone calculator, turn it sideways, it expands it, makes it bigger. You've got the log and the natural log buttons. So you got those buttons over here. These are the common logs. They're common. They have their own button. So log base 10 of 81, close parentheses, divided by log base 10 of 3 gets me the same number as the log base feature does. If I do natural log the same way, it works. And then, so log base 3 of 24, I could do the same ways. I could use common logs to get those. But the base always goes in the bottom. That's the way I remember the change of base formula. That the base of the log that I'm trying to evaluate always goes in the bottom of the fraction. And sometimes it's quicker to just type those in than it is to get to hunt down the log base and get that. But that's the change of base formula. So maybe file that away somewhere, but you might need that eventually. I don't know. Can make manipulating things a little easier. All right, let's talk about the title of the lesson was functions, logarithmic functions. So let's talk a little bit about functions, and that relates to domain and range and all that stuff that we've done with functions in every section that was some sort of function. F of x equals log base a of x. So that's our basic thing. Domain in general is only positives. So in this case, we would set x greater than 0. So whatever we're taking the log of, we're going to set greater than 0 to find the domain. So if there's something else in there, we're going to do something that have other things in there. Set that greater than 0, solve it. That's going to give you your domain for that particular log function. The range is going to be from negative infinity to positive infinity.
Justin White and Anna Kate D. Berry report to the library.
Here's the thing. Exponentials, when we did those, the domain of every exponential was what? All real numbers, negative infinity to positive infinity. So on those two on the quiz, I hope that's what you put for domain. Negative infinity to positive infinity, okay? The range was dependent upon where that horizontal asymptote was, right? And then it went up or down depending on what the signs were in there. A logarithm is the inverse of a exponential. Okay, so here, what does an inverse do? Swaps x and y, swaps domain and range. So here, this range is the domain of the exponential that this was. Okay, and then the domain is the range based on what that horizontal asymptote was on the exponential. So logarithms and exponentials are inverses of one another. That's why we can use them to solve the other one. So I can use a logarithm to solve an exponential. I can use an exponential to solve a log. That's the inverse property there. All right, so that's where those are coming from. So let's look at some logarithmic functions that are a little bit different and talk about domain and range of them, so we get some experience with that. So just state the domain and range. All right, simple n. F of x is equal to log base 2 of x plus 3. It doesn't really matter what base the log is. It could be log base 2. It could be log base watermelon. It really doesn't matter what the base of the log is as far as finding the domain of that particular function. So domain, logarithms, we can only take logs of positive numbers, so we're going to set that greater than 0. So we say x plus 3 is greater than 0 to find the domain. I'm going to write that down here. Domain. X plus 3. Whatever you're taking the log of, set it greater than 0 and just solve it. So that'd be x is greater than negative 3. So our domain, all x's as long as x is greater than negative 3, or parentheses negative 3 to infinity. Both of those would be, there's our domain. Our range, negative infinity, positive. You really got to think about that. We could look at the graph of that if we wanted to. Hit y equals, clear out some of this exponential stuff I was doing the other day. I'm going to hit math, get the log base 2 of x plus 3. Graph. I'm zoomed way out. There we go. And resolution kind of fails us here that this gets fairly vertical here because there's a vertical asymptote with a logarithmic function where there was a horizontal asymptote with a exponential, right? So they're inverses of one another, so that's going to swap. So there's a vertical asymptote right there. What's happening at -3. And thus we see the domain going toward positive infinity there. So you can graph it and get a good idea of what should be happening there. All right. Let's look at one that's slightly more complicated. Example O of x is equal to log base 5 of 1 plus x over 1 minus x. So a rational expression inside of a logarithm. And we're asked to find the domain and the range of that. So range, I got that in my pocket. That's easy. Negative infinity to positive infinity. That's a given. Domain, a little bit more difficult. We're setting a rational function greater than 0. Okay. Rational functions, when you're dealing with them as an inequality, you have to set up intervals to find their results. Okay, and those intervals are going to be, where's the top part equal to 0? -1. Where's the bottom part equal to 0? +1. So we have a -1, we have a +1. Those are open circles on those spots because this is it's a greater than symbol, no equal to mark. If it were an equal to mark, you'd have filled ins on the numerator part. Always open on the denominator anyway. Okay. And then we need to test values in these intervals that this creates. That's how you solve a rational inequality. So intervals, so I need something less than -1. -2 is a good number to plug in. And I test it in the inequality. 1 plus -2 is -1. 1 minus -2 is 3. So we have -1 over +3, which is a negative fraction, right? Is that greater than 0? No. So this area is false. So we know that's not part of the domain. Okay. Pick a number between -1 and 1. 0. That's a wonderful one. 1 plus 0, 1 minus 0. 1 over 1 is greater than 0. So it's true in between there. Okay. That may be the only interval that's true. It could be that this one is too. We just skip the 1. Okay. So plug in a number that's bigger than 1. 2 is good. 1 plus 2 is 2. 3. 1 minus 2 is -1. 3 divided by -1 is -3, which is not greater than 0. So that is a false area there. So the only spots for the domain to work are all x's that are between 1 and +1. So there's the set notation for that. Interval notation I think is easier. -1 to 1. A rational function, we want to set that up there. Okay. That's looking at a rational expression inside of a logarithm. Again, the base of the log does not matter. Doesn't change how you do that. It's just going to change how fast the curve turns. That's what the base is going to change. Okay. Let's look at another one. Something we maybe haven't done in a while is an absolute value in there. So f of x is equal to log base 3 of the absolute value of x. Okay, if we're going to find the domain, take absolute value of x, set it greater than 0. What do we know about absolute value and greater than 0? Absolute value is always positive numbers. That's true. Okay, so what number is thrown out? What's only 0 is the only one we can't have, right? So all x's that are not 0. From -infinity to 0 union 0 to positive infinity would be the interval notation for that. And range, negative infinity, positive infinity. All right. So absolute value, setting that up, you're going to set up this inequality. Remember, greater thans are ors. So when you set that up, let's do one that's got a little different number in it, just so that I'll make sure you remember how to do those, because it's been a while. Let's do log base 13 because that's fun. It doesn't matter. When you set that up to do domain, you're saying the absolute value of x plus 2 is greater than 0. In Algebra 1, we learned that when we're solving those, you're setting up two inequalities, that x plus 2 is greater than 0, or, because it's greater than, x plus 2 is less than 0. Okay. Ends up being negative 2 is the only number that's thrown out there, right? So domain, x can't be negative 2, negative infinity to negative 2 union negative 2 a positive infinity. And then the range we know is still the same. Easy stuff. All right. Let's look at solving a few equations to finish up with. Got plenty, just enough time, I think, to do that. Solve. So again, the idea in this section is not necessarily working with logarithmic properties, but with the conversion between logs and exponentials. That we get a logarithmic equation, we need to think about it as an exponential equation. So how do I rewrite this logarithm as an exponential? Yeah, 3 squared is equal to 4x minus 7. And that's an easy problem to solve then, because 3 squared we know is 9. And we can solve that. So plus 7, 16 equal to 4x, x is equal to 4. The only thing we need to do is check that in the original log to make sure that's not 0 or a negative number that we're taking the log of, because it came from a logarithmic equation. So 4 times 4 is 16, 16 minus 7 is 9, and that's okay to take the log of a positive 9. Okay, so you need to check your solutions when you're working that. Let's say we had log base 3 of 3 to the 6x is equal to 42. We think about that as an exponential. 3 to the 42 is equal to 3 to the 6x, which is exactly what we did yesterday and the day before. Bases are now the same. Hey, 42 is equal to 6x, so x is 7. If I plug that in, I know 6 times 3 to the 42nd power is going to be a positive number. We had an exponential equation given to us. We know how to do that, right? We know that that's 3 to the 4x, and that's 3 to the third. Here's how the logarithm relates to that. We've just been dropping the bases and having 4x equals 3. The math that makes that work is that you actually take the log base 3 of each side. And the 3 as the base and the log base 3 cancel each other out. That's the logarithmic property that's happening there. The same thing happens here if you just set up, hey, those two can cancel and you get 6x equals 42. It's the same equation. The theory is the same. The mathematical property that's happening there is taking the log base 3 of each side to get a solution. Where that comes into play is when you have a number that's not a nice base of 3, like we did earlier when we had 3 to the 5x is equal to 24. Let's say that's our equation. 3 to the 5x equals 24. Well, I can't write 24 as a base 3, right? That's the problem. So to get rid of this 3 here, I've got a 5x up there. I know the variable's in the exponent. To get rid of the base 3, I can use a log base 3 on each side. If I use the log base 3 of 24 is a number, right? We know we can put that in calculator, get a decimal. It's an ugly decimal number, but it's a number, right? So I can take that and plug that in. And on the left-hand side, the log base 3 and the 3 cancel out. And I just get 5x is equal to log base 3 of 24, right? And that's a number. How do I get x by itself? Divide everybody by 5. So I divide that whole problem over there by 5. The exact solution is log base 3 of 24 is over 5. And then we could work that out with a calculator if we needed to. So we could do math log base 3 of 24. Get that answer, divide it by 5, and there we get the decimal approximation for that. So 0.5786. Page 445, 9 through 110. A lot of problems there, but just do the odd ones. Okay. And that'll get you what you need for class. All right. You guys have a great day.